is
Let's get into it.
Space-Time Curvature. You hear about it all the time.
Okay.
You hear these fancy physics guys saying space-time is curved by mass, but what's happening, okay? Well, space as we know it is three-dimensional, and time, we consider it as a fourth dimension, and then we exist on this four-dimensional manifold. And it's not actually the space that's curving, right? It's the space and the time together, right? That's curving. So, for example, one way that you can peer into like more complicated topics in physics is to analyze light, because light for a very long time, and it still is, pretty mysterious, and it's actually hard to study, right? Because imagine you have no tools and someone was like, okay, like do an experiment with light. It's like, all right, it's kind of difficult.
It is.
But for example, something that they did do actually when general relativity was hot on the block, right? Just dropped. Everyone was like, all right, we need to see what's actually happening with general relativity. They had this whole event where a bunch of astronomers got together. I think it was this whole international thing, and they looked at an eclipse of the sun, a solar eclipse. And as predicted by general relativity, you could see stars that were actually behind the sun. How is that possible? Well, actually, the path that the light took actually went towards the back of the sun, right? And then curved around it into our eyes. And so it was actually one of the first confirmations that, Einstein's theories weren't just, they weren't just words on pages. It was actually like, okay, these stars are supposed to be hidden by the sun, but the light that came out of these stars was actually curved around. The path of the light was curved around the sun. And so, boom, there we go. Now we know that space-time curvature is actually a thing.
And another way to think about it is also think about Newton, right? Now, Newton says F equals GMM over R squared. Or, for those of you that might not be up to date with the latest equations, force is proportional to mass, right? The force of gravity is proportional to mass. Now, light happens to have no mass. So, by Newton's laws of gravitation, light should not be touched by any massive object, right? Or so gravity should not be able to control light, basically, is what Newton would say. However, that's not true, because remember, gravity is not even a force, right? That's the whole idea behind the paper. And I think he puts it in a very succinct way, especially with the whole, because it's a very big thing to say. Newton was, not that the force idea is wrong, it's just that Einstein's principles and his understanding of space and his representation of space agrees with Newtonian mechanics. It should.
It does.
It's not it's not like you can't use Newton. It's not like it's wrong. It's just that on a fundamental level, that's simply not what gravity is. You can calculate the force. You can understand it as a force, because in that one episode, we spoke about how force and acceleration are related, right? And how acceleration is the key behind understanding the force. The only reason we say there's a force is because of the acceleration. So Einstein is like, yeah, there's no force. There's still acceleration. So that relationship is still there. And that's that Newtonian relationship. That relationship, force, acceleration, it's still there. But we don't care about the force part. We just care about the acceleration. And I'm saying the acceleration depends on the mass of the body it's surrounding, right? So like, for example, on Earth, now you were even talking about time and how time bends along with this space thing, right? And a lot of people, might think, well, that's very interesting. Like, how does time also bend? Well, it's in a very similar fashion. Now, obviously, it's not a physical thing, but it bends in terms of slowing down or speeding up. So when you're near, like a massive object like the Earth, for example, a spacecraft, let's say it's traveling completely straight line, there's nothing, absolute vacuum, it's just traveling in space, and then all of a sudden it encounters Earth. the time that the spacecraft experiences while encountering Earth technically is slowed down with respect to Earth. So Earth before, when it was in a vacuum, versus Earth when these guys are actually traveling through it, in that gravitational field, that's when their time slows down. So that's how time is also wrapped up in this whole shenanigan, right? And that's a very fundamental thing. I think that was even bigger of a thing that he proved, how time is related to all of to space.